This lesson is about relations and functions. You may not be familiar with the word function, but perhaps you are familiar with the word relation and words similar to that, such as related to or relationship. There are many things that have a relationship. For example, mothers and their children have a relationship. You might have a relationship expressed by is the son of, where you would express the mother and the son. In mathematics, we generally talk about relationships that exist between numbers. First, we're going to look at the definition of a mathematical relation. A relation is a set of ordered pairs. The domain of the relation is the set of all first coordinates, and the range is the set of all second coordinates. So first of all, we see that when we talk about a relation in mathematics, we're simply talking about a set of ordered pairs. Usually in mathematics, that means a set of ordered pairs of numbers. We looked at the Cartesian coordinate system in a previous lesson and learned about ordered pairs and how we can picture those ordered pairs on a graph. We also learned that ordered pairs often represent the solution to an equation. Any set of ordered pairs is called a relation, and we usually say that the second coordinate is related to the first coordinate through some rule that is given. Recall that there were two special names associated with this relation. The domain of the relation is the set of all of the first coordinates of those ordered pairs, and the range is the set of all second coordinates of those ordered pairs. Let's look at ways of defining a relationship in mathematics. Ways to describe a relation between two sets, X and Y. I have chosen to let set X be the numbers 1, 2, 3, and so forth up to the number 10. Y is the set of numbers 3, 4, 5, and so on up through the number 12. If we give a roster simply means a list. You'll notice in this set we have listed ordered pairs. We have paired the number 1 with the number 3, 2 with 4, 3 with 5, and so on in this same pattern until we finally pair 10 with 12. Notice that our first coordinates are 1, 2, 3, and so on up to 10. These are the numbers that came from set X. So the numbers in set X would be the domain of this relation. The second coordinates are the numbers 3, 4, 5, and so on up through 12. Or in other words, these numbers in set Y are the numbers that would constitute the range of this relation. So one way to describe a relation is to simply list the ordered pairs that belong to that relation. A second way of describing a relation is to give a rule or equation that describes the relationship that exists. Notice in this rule we have that y equals x plus 2. So how is y related to x? Y is exactly 2 more than x. Look at your ordered pairs. 2 more than 1 would be 3. 2 more than 2 would be 4. 2 more than 3 would be 5, and so on until finally 2 more than 10 would give you 12. So this rule describes the relationship that exists between these numbers that are in the ordered pair. The final way of describing a relation is through a set notation like this. Let me read this for you. S is equal to the set of ordered pairs X, Y, such that Y is equal to X plus 2 and X is an element of set X. Notice that we read this symbol, of course, the set of, which you have probably seen before. The set of ordered pairs X, Y. The colon is read such that. Following the colon, we're going to give a rule that tells the relationship between x and y in this ordered pair. Y is going to be twice or 2 more than x, or x plus 2. And then sometimes following this rule, we will tell you where the numbers x are coming from. X is coming from these numbers in set x up here. You can see that all 3 of these ways describes the same set. Let's look at an example. Write the following relation as a set of ordered pairs. We want the set S to be the set of ordered pairs x, y, such that y is equal x squared minus 5. And notice here, x is equal to the numbers -3, -1, 0, 2, and 5. So let's write down the set of ordered pairs. We will use our first number for x, -3. Recall that x is usually written as the first coordinate. Now, if we use -3 in this equation, -3 squared would be a positive 9. 9 subtract 5 would give me a y value of 4. So my first ordered pair consists of -3, 4. Now we'll place a comma to separate these ordered pairs, and we'll go to our second value for x, -1. If x is -1, if I square -1, I get positive 1. Positive 1 subtract 5 would be -4. My second ordered pair is -1, -4. My third value of x is given to be 0. Substituting 0 for x, 0 squared, of course, is 0. And 0 subtract 5 is -5. Then we'll use the number 2 for x. 2 squared is 4. 4 subtract 5 gives me -1. And then finally, my last number for x is 5. 5 squared is 25. 25 subtract 5 would be 20. We have used every one of the x values that was given to us, and we have written the corresponding y value that comes from this relationship. Now, let's identify the domain of this relationship. The domain consists of the set of the first coordinates. The first coordinates are -3, -1, 0, 2, and 5. You might recognize that these numbers are the same numbers that were given here for x. So a lot of times we associate the domain with the x values. Keep in mind, however, that we do not have to use the letters x and y. So if we were using different letters, we would not want to say that the domain is the x numbers, but rather the first coordinates as was given in the definition. Notice also that when you use this type of notation, after you say the ordered pairs and you give the rule that gives the relationship that exists so that we may find the second coordinate that is paired with the first, sometimes after that we list the domain of this relation. Now we will see in a later example that there's not anything written for this domain, and we'll explain at that point what you do if there is not a domain specified. Now let's also list the range for this relation. The range, recall, consists of the second coordinates of our relation. So listing our second coordinates, that would be 4, -4, -5, -1, and 20. Now that we have seen what a relation is, we are ready to define a function. Functions play a very important role in mathematics. If you continue your study of mathematics, you'll find that you look at functions all the way up through college algebra and calculus, and even in trigonometry, you talk about functions. Let's look at the definition of a function and then we'll discuss it a little bit farther. Functions. A function consists of two sets of real numbers called the domain and range, and a rule or formula that assigns to each element of the domain one and only one element of the range. Now, another way of saying this same definition is to say that a function is a relation such that no two distinct ordered pairs have the same first coordinate. Now, why would we say that a function is a relation? Well, let's see what's happening up here. A function consists of two sets of numbers called the what? Domain and range. We've discussed domain is the first coordinates and range is the second coordinates. So it's implying here that we have a set of ordered pairs, doesn't it? We have a rule or a formula that assigns to each element of the domain one and only one element of the range. So our formula is assigning an element from the range to the domain, or it's creating ordered pairs. So a function is a relation, is saying that a function is also a set of ordered pairs, just like a relation was. But notice that there's an additional criteria here. No two distinct ordered pairs, that means two different ordered pairs, have the same first coordinate. In other words, the first coordinates in these ordered pairs cannot be repeated. You may not have, for example, 2 paired with 4 and also 2 paired with 5, because that same first coordinate of 2 would have 2 different second coordinates, and that would not be allowed in a function. Notice also in this domain, to each element of the domain we assign how many? Only one element from the range. Students sometimes have difficulty with this idea of a function and knowing how to determine if a given equation that describes a set of ordered pairs is a function or not. I would encourage you to think about it like this. Given an equation, if you choose a first coordinate, and many times that means choosing x because we so often use x and y, but choosing that first coordinate and putting it into that equation, you want to know how many answers can I get for the second coordinate, which is usually y. If I can only get one answer, then I have a function. But if I can get more than one answer, then I do not have a function. We'll try to expand on that idea as we look at some examples. Here we want to find the domain and range of the relation below and determine if the relation is a function. We'll notice this is written f equals the set of ordered pairs x, y, such that y equals 3x minus 2. Now, what's different from this one than the way we saw this set written a little while earlier? After this equation in the other example, we had x values given. Here there are no x values given. In fact, we're supposed to find the domain. So generally what we do is this. If there is no domain specified, we assume that the domain consists of all real numbers for which the given equation would be defined. So you might want to look at this equation and thinking about we're going to choose x, which will be our first coordinate here. What kind of numbers can you choose for x? Is there any restriction on that? Well, I see that I could certainly choose any kind of positive or negative number for x and be able to do this arithmetic. I could choose fractions. I could choose decimals. I could even choose things like the square root of 2 and be able to do this arithmetic. So it appears from this equation that my domain consists of any real number. And sometimes we will say it like that. My domain is any real number. And we may just write that out. Or you could say the set of all real numbers. I'm going to abbreviate this time. Or sometimes we used a script letter R to be a shortcut way of saying the set of all real numbers or any real number. So however you want to write this, the domain of our relation consists of all real numbers because we may choose any number for x in this equation. Now sometimes determining the range from the equation is a little bit more difficult. You might want to think here, what kind of answers do I get for y? Because recall, the range is those second coordinates. Well, I can see that if I choose a small enough number like, let's say 0 here, I can get a negative answer. But if I choose x large enough, 3 times x will be big enough that when I subtract 2, I can get positive answers. So both negative and positive answers are possible here. If I choose fractions for x, I may get fractional answers. Just looking at the equation and thinking about the types of answers, I'm tempted to say that my range also might be any kind of real number. Now, what we're going to do is to look at the graph in a few moments, and we'll be able to see from the picture of the solutions of this equation that in fact the domain and range is all real numbers for this relation. Now, let's see if we can answer the question, is this relation a function? So, recall what I suggested. Think about, if I choose a number for x, in fact, let's just choose a few here. If I choose x to be 0, substituting 0 here, 3 times 0 is 0, subtract 2 would give me a negative 2. When I chose this 0 for x, how many answers was I able to get for y? I only got one answer, didn't I? Well, let's try another number. Suppose I choose x to be 2. Well, putting a 2 in for x, 3 times 2 is 6. 6 subtract 2 gives me 4. Again, I'm only going to get that one solution whenever I choose x to be 2. Let's choose x to be, let's say, 3. 3 times 3 is 9. 9 subtract 2 gives me 7. Again, I'm only getting one answer. Let's choose a negative number here. If x is negative 1, 3 times negative 1 would be a negative 3. Negative 3 subtract 2 would be a negative 5. Again, how many solutions did I get? I only got one. It looks like that when I choose a number for x, I'm going to multiply by 3 and subtract 2. I'm always going to get only one answer. In other words, for any given first coordinate, there will never be two different answers. That tells me that this is a function. Now, since I have some ordered pair solutions to this equation, let's graph those. I have 0, negative 2, positive 2, positive 4, positive 3, 1, 2, 3, 4, 5, 6, 7, and negative 1, negative 5. Now, you probably suspected from previous lessons that this graph was going to be a straight line because that equation that we were looking at was a linear equation, wasn't it? Excuse me. Now, let's look at this graph. Recall that our domain is all of the first coordinates. In our ordered pairs, the first coordinates mean the x values. Now, this is the x-axis. Think about as you move to the right on the x-axis, any of these x values. If I choose this x value, notice there's a point down here on that graph. If I choose this x value, there's a point up here on this graph. If I choose an x value over here, although if I go up from that point, I can't see the point on my graph, because this graph continues to go on up, eventually this line up above this x value, there would be a point on that line. If I move to the left for any given x value, I can move down to this line. There will be a point on that line for that given x value. So my domain is indeed any real number, because any number on this x-axis is going to have a point on the graph associated with it. Now, for our range, the range is the y values. The y-axis is this vertical axis. So again, think about it, as I move on this vertical axis, is there a point on the graph across from any given y value? And I think you can see that there is, because again, this line will continue to go up. As I move up on the y-axis, there will be a point over here somewhere corresponding to that y value. So there will be a point on the graph for any real number as a second coordinate of this relation. Did I have any ordered pairs where the first coordinate was repeated? Recall that in your definition, if I have two different ordered pairs, they cannot have the same first coordinate. If 2 points have the same first coordinate, let's just say, since I've kind of written on this, let's say we have the x coordinate of -4 and the y coordinate of 2. If I have another ordered pair with that same x coordinate of -4, let's say the y value, however, is a +4. Notice those points would be in a vertical line from each other. Are there any points on the graph of these solutions where these points are in a vertical line? Or in other words, the points would have the same first coordinate? No, there is not. So this is a function. Let's look at a second example. Find the domain and range and determine if the relation is a function. R is the set of ordered pairs xy such that xy is equal to, such that y is equal to x squared plus 2. Let's talk about the domain. Nothing was specified about the domain of this function. Think about choosing x values here. Could you choose positive numbers for x? Yes, you could. Could you choose negative numbers for x and be able to do this arithmetic? Yes, you could. Could you choose fractions? Certainly. Could you use stuff like the square root of 2 and work this equation? Yes, you could square the square root of 2 and then add 2, couldn't you? I can't seem to find any restriction on this x value. I'm going to write that the domain of this relation can be any real number. Now, let's talk about the range. What kind of answers will I get? Well, let's see. If I choose some numbers, in fact, let's just choose a few while we're doing this. What if I choose x to be 0? 0 squared is 0 plus 2 gives me 2. If I choose x to be 1, 1 squared is 1 plus 2 gives me 3. If x is 2, 2 squared is 4 plus 2, I get 6. Obviously, if x is a positive number, if I square it and add 2, my answer is also going to be positive, isn't it? What about if x is a negative number, like, for instance, -1? What happens when you square -1? Don't you get a positive 1? Positive 1 plus 2 is 3. If x is -2, if you square -2, you get positive 4. 4 plus 2 is 6. We could, of course, continue this. But have you noticed that it will be impossible for us to get a negative answer for y? If we're squaring x, that will always be a positive number or perhaps 0. And then we're adding 2. We can never get a negative answer. In fact, looking at these y values, I noticed something else. If the smallest value that x squared can have is 0, and 0 plus 2 gives me 2 for the y value, I believe that the smallest y value will be 2. I think my range is going to consist of y values that are greater than or equal to. Now, if we want to write our range as a set, we may say the set of numbers, what? Real numbers greater than or equal to. We could also name this range as an interval notation like this. This means with the bracket that 2 is included in the set, and we go from the number 2 to positive infinity. That symbol means that we go on and on and on without ever stopping. Any of these three notations would be a correct way to write the range of this relation. Now, is this a function? If we put in a number for x, like 0, how many answers did I get? I only got one answer. When I put in 1, I only got one answer. When I put in -1, I only got one answer. For each x that I put in, I only get one answer for y. Or looking down the list that we have started, do any of these ordered pairs have the same first coordinate? No, they don't. This is a function. Now, this is the kind of function that sometimes confuses students. Notice that over here, we do have our second coordinates that sometimes are the same or repeated. That was not in the definition. Look again. A function is a relation such that no two distinct ordered pairs have the same what? First coordinate. It does not say anything at all about having the same second coordinate. So it's okay to have the same second coordinate, just not the same first coordinate. The x values are the first coordinates, do not repeat. Again, let's look at the graph of this relation. We have the point 0, 2, 1, 3, 2, 6. Then we have -1, 3, and -2, 6. We have graphed these before. Recall, this is a curved line in both directions. It is not a straight line. And this graph, remember, we said, had the shape that is sometimes called a parabola. Now, let's look at this idea of domain and range and function again from the graph. As I move on the x-axis from left to right, I want to know, will there be a point on this graph above any of these numbers for x? Notice the arrows that I placed here. This curve is going to continue to go up. Now, it's going to get very steep, but it's going to go up forever. And notice it doesn't ever go straight up in a vertical line. It continues to curve outward. So, even though it may take a while, above this number x right here, for instance, eventually, way up here, there will be a point on that graph for that x value. So x certainly is any real number for this equation. But notice, on your y-axis, these y values down here below a y value of 2, there is no graph. And there never will be a graph, because this graph is opening from this point and continuing to go upward. The smallest y value that we encounter on this graph is at y equal 2. So our y value can be equal to 2 or it may be bigger than 2, but never smaller than 2. So we did have the correct range here. And again, you can see that there are no 2 points that have the same x value or x coordinate. So this is indeed a function. Having looked at these 2 examples, I want to give you now what's referred to as the vertical line test to determine from a graph if you have a function. Our vertical line test says if any vertical line crosses the graph of a given relation more than once, then the relation is not a function. Any vertical line means a vertical line that we can place anywhere on that graph. And our test is, does the vertical line cross the graph more than once? If it does, we do not have a function. Let me come back to this example that we did a moment ago. If I do a vertical line, notice it only crosses this graph once. If I place a vertical line here, it only crosses that graph once, doesn't it? A vertical line will never cross this graph more than once. So from that vertical line test, we have a function. Let me go back also to the first example we did here. If you take a vertical line and cross this graph, it's only going to cross it once, anywhere that you place that vertical line. So this indeed is a function. Sometimes it's easier to determine from the graph using this vertical line test whether or not you have a function than it is simply by looking at the equation. Find the domain and range and determine if the relation is a function. What I'm going to do here is to first of all take this equation and rearrange it a little bit. Recall, when we find the domain, we want to know what is the values that we can use for the first coordinates. The x values are the first coordinates. Usually, if we have our equation solved for y, then we can tell about these x values. Notice my equation says y squared is equal to 5 minus x. How do you solve for y if you have y squared? Well, you have to take the square root, don't you? But remember, there are 2 square roots of every number. One number is positive and the other number is negative. If I solve this equation for y, I have to say that y is going to be either the positive or the negative square root of 5 minus x. Now, sometimes it's easier to look here and notice if I'm going to take a square root of this quantity here cannot be negative, can it? If I try to take the square root of a negative quantity, I get a complex or imaginary number, which is not a real number. And remember, when we talk about functions, we have to be doing ordered pairs of real numbers. I need 5 minus x to be greater than or equal 0 so that it will not be negative. Now, I can solve for x by doing this. If I subtract 5 from both sides, I have that negative x must be greater than or equal negative 5. I would like to change this x into a positive rather than a negative. Remember, I can accomplish that by multiplying both sides by negative 1. But if you have an inequality, when you multiply both sides by negative 1, you reverse the direction of the inequality. X must be less than or equal positive 5 in order to get a positive number under this square root. If x must be less than or equal 5, we have just identified here our domain. I'm going to use a D to represent domain. So our domain, x must be less than or equal 5. We can say that as an interval. If we are less than or equal 5, we are from negative infinity up to 5, including 5. Or we may write as a set the real numbers less than or equal 5. Now, let's see if we can find some ordered pairs before we talk about the range or whether or not this is a function. Let's choose 5 for x. And I don't really care if you look at it here or here. If we choose 5 for x, we get a 0 under this square root. The square root of 0 is 0, and it doesn't matter whether that is positive or negative. And again, if you look here, 5 subtract 5 is 0. If y squared is 0, y must be 0. If I choose x to be 4, 5 subtract 4 is a 1. The square root of 1 is either positive 1 or negative 1. So notice that when I choose x to be 4, I'm getting two possible answers here. And looking at it here, if I choose x to be 4, 5 minus 4 gives me a 1. If y squared is equal to 1, then isn't it true that y can be either positive or negative 1? Now you might notice right here, I have two different ordered pairs here that have the same first coordinate. Can this be a function? No, this is not a function, and we'll illustrate again with the vertical line test in a moment when we go to the graph. Let's choose, how about x to be 1? If x is 1, 5 minus 1 gives me a 4. What is the square root of 4? It's 2. Y can be either 2 or, remember, negative 2. Again, if we choose x to be 1, 5 minus 1 is a 4. If y squared is 4, y could be either 2 or negative 2. Now, just to be sure you understand about this domain, what if I choose a number bigger than 5? And I'm going to put it over here. If I choose 7, y squared equals 5 minus 7. Can y squared equal negative 2? No, it can't, can it? So we cannot use that 7, can we? Let's plot these points that we have found. I have 5, 0. I have 1, 2, 3, 4, negative 1. I have 4, positive 1. I have 1, 2, and I have 1, negative 2. Now I might illustrate, we haven't chosen a negative number for x yet. Let's choose x to be, let's say a negative, I'm trying to pick something that will be easy, 4. 5 minus a negative 4, that's going to be a plus positive, is going to give me a 9. What is the square root of 9? It's 3. Could be positive 3, could be negative 3, couldn't it? So if x is negative 4, 1, 2, 3, 4, I have a positive 3 or a negative 3 here. This is one of those parabolas that is kind of on its side like we looked at in a previous lesson also. Now, notice on your graph, there is going to be no graph to the right of this x value of 5. So our domain certainly does not include any x values to the right of 5. So we were correct by saying that our domain must be any real numbers less than or equal to 5. What about our range? Think about your y values. Across from these y values, there's certainly points on the graph. What about down here? If I go out this way, because this is going to continue to slightly go downward as it goes, and this will continue to slightly go upward, we will eventually have a graph for any y value. Our range is any real number. Now, recall the vertical line test. If I draw this vertical line right here through my graph, notice there are two places that vertical line crosses my graph. According to the vertical line test, if any vertical line crosses more than once, then it is not a function. We, of course, determined earlier not a function because we had these ordered pairs here, and of course here's other examples where we have the same first coordinate. And of course, having the same first coordinate is what created these points that were in a vertical line from each other and caused this vertical line to cross our graph more than once. So for this problem, our domain is real numbers less than or equal 5. Our range is any real number, and it is not a function. I have one other example that I would like for us to look at. Find the domain and range and determine if the relation is a function. Our equation here is y equals the square root of x minus 2. Let's talk about our domain first. Now in this problem, notice that the square root was already written in the problem. So first of all, this quantity under the square root sign cannot be negative. We need x minus 2 to be greater than or equal 0. Solving for x gives me x is greater than or equal to. This identifies my domain. And I can say that again in the interval notation as being from 2 to infinity, or in set notation as any real number greater than or equal to. Before we find some ordered pairs and talk about the range and whether or not we have a function, I want to remind you that this square root symbol without any signs written in front means the principal square root. The principal square root means the positive square root. So here we are only looking for the positive square root. Let's choose some values for x from this domain. Let's start with our x value of 2. 2 subtract 2 is 0. The square root of 0 is 0. Let's choose x to be 3. 3 subtract 2 is a 1. The principal square root, or the positive square root of 1, is 1. We do not want to put down negative 1 here because y does not equal the negative square root because there's no sign to indicate that. Let's see, I'm trying to choose numbers here that will be easy to graph. Let's choose x to be 2 for our next value. 6 subtract 2 gives me a 4. The square root of 4, the principal square root of 4, is positive 2. What would be another good number to use here? I can take the square root of 9, can't I? What number subtract 2 would give me 9? 11. 11 subtract 2 gives me 9. The principal square root of 9 is 3, and we can continue this. Let's graph these points. I have 2, 0, 3, 1, 2, 4, 6, 2, and of course 11, 3 won't fit on my graph. We've looked at this graph actually before in a previous lesson. Our graph looks like this, doesn't it? You can see there's no graph to the left of x equals 2 because those numbers are not in our domain. Let's answer the question now about the range. What kind of y values are we getting here? Notice that from our graph, there is no graph below the x-axis, is there? That's all those negative y values. Why are we not getting negative y answers? Because y is equal to the principal square root, positive square root. Y is not going to be negative from our equation. Now notice we can get a y value of 0, and then from there our y values are increasing. Because this graph will continue to slowly rise as we continue to choose these x values, our y values are going to also continue to increase. Our range for y will always be greater than or equal 0. As an interval, that means from 0 to positive infinity, or as a set notation, any real number greater than or equal 0. That is our range. What about, do we have a function here? I never did see any ordered pairs that had the same first coordinate, but obviously from this graph, if I pick any vertical line anywhere on this graph, it will only cross the graph one time. It will never cross it more than once. So, yes, this is a function. I hope that after having looked at these values here and these examples, that you have a better understanding of relations and functions. In order to have a function, you have a set of ordered pairs where your first coordinate is never repeated, or these ordered pairs do not have the same first coordinate. Or, in other words, if you choose a first coordinate, you will always get only one answer for that second coordinate. If you graph your relation, you can tell using the vertical line test whether or not you have a function, or sometimes it's easily determined from the equation. Your domain is the set of all first coordinates. Your range is the set of all second coordinates. And again, sometimes you can determine that domain and range easily from the equation. Sometimes it is easier to tell that information from the graph. This completes the lesson on relations and functions. I would appreciate it if you would rewind this tape before you return it to the math lab. Thank you very much.